Hello and welcome to another video on my channel. In this tutorial I'm going to talk about complex numbers, because complex numbers are an extension to the real numbers, and by default Java only works with real numbers, integers, doubles, floats. So in order to have complex numbers we have to write a class, an object that represents the complex numbers. Now, what is a complex number? A complex number is basically a two-dimensional number. So basically it has a x coordinate and y coordinate, and we typically represent the complex numbers on the complex plane or z plane. So it's called the complex plane, and the horizontal axis is the real part of the z, and the vertical axis is the imaginary part. And what do I mean by real and imaginary part? There's a number j that is called the imaginary index, okay, and that's a purely imaginary number, and it's a unit number, so its magnitude is 1, and it resides on the positive direction or positive part of the imaginary numbers. Okay, so a complex number has a real part, which let's call it x, and an imaginary part, let's call it y. Okay, and these numbers are presented on the 2D real imaginary plane, or sometimes called the complex plane or the z plane. Z is a typical name for representing complex number. J is informally defined as the square root of the -1. So we know that the square root of -1 doesn't have any value in real numbers. So this is definitely not a real number. That's why we call it purely imaginary. Okay, but this is an unofficial or informal definition. So this is more like informal definition. A more formal definition requires more of a advanced math of how to define groups and this kind of stuff, but most engineers don't bother with that because it doesn't have any practical value to know the details. We just consider j as a purely imaginary number, and any complex number can be constructed by adding a real number to a purely imaginary number. Okay, and since the informal definition of j or the imaginary index is the square root of -1, it means that j times j or j squared is -1. This is the fundamental property of j. So j squared is a real number, -1. And the complex numbers, for real numbers we usually use x and y. For complex numbers we usually use v, u, w, z, these kind of parameters, variables to represent complex numbers. And then because the complex number is basically assigned to a point on a plane, on a 2D plane, so z plane is two-dimensional, we can also consider or assume a length or a distance from the origin, right? From the origin of the coordinate system, the origin of the 2D plane. And that's just equal to a square root of x squared, this distance x, plus y squared. This is just the Pythagorean theorem. So distance from origin is basically the modulus or the magnitude of z. So I'm going to write it down, magnitude. Okay, it's called the magnitude. And there is another very commonly used definition, which is the conjugation or the conjugate of a complex number. So the conjugate or the complex conjugate of a number, a complex number, is that you just reverse the sign of the imaginary part. So the real part stays the same, the imaginary part is just multiplied by -1. Now in more general case, pretty much in your number, wherever you have j, you change it to negative j. So I'm going to write it down. Pretty much j becomes and wherever I have j, I convert it to negative j in my complex number. And this is equivalent to saying that you just take the imaginary part and then multiply it by -1. So the complex conjugate of x plus jy, assuming that x and y are real numbers, is just x minus jy, okay? And let's maybe just remove this multiplication sign. And as I mentioned, typically real variables, real numbers are denoted by x and y. Complex numbers are denoted by z, x plus jy. And the key thing is that Java doesn't support complex numbers by definition. These are structures, these are not primitives, okay? Other languages such as Python, they have a built-in complex functionality, so you don't need to implement it again. But Java doesn't do that. So the approach we take is to define the complex numbers as an object, and they hold the data of the real part and the imaginary part, okay? So a number, and when we are going to do this, define numbers as an object, we have to consider that if I define a complex number, I should not be able to mutate it, so no mutation. So no mutation is allowed. I shouldn't have a setter to, for example, change the real part without changing the imaginary part. Basically, when I have a complex number, the only thing that I can do is to assign a new number to this complex object, just like strings, right? When you define a string, you cannot mutate it, but you can assign a new string to the original string, okay? And in order to do that, just like the Java API for a string class, you have to define as a final. So it could be defined, a complex number can be defined as a final object, a final class. So no one can extend it or override any of the methods, nothing. The only thing that the user can do is to assign a new complex number to a complex object, okay? Now the other details are that each complex number, in addition to the modulus or the magnitude, we can define a phase that represents the angle of the point that the complex number is pointing to with respect to the horizontal axis. Sometimes we call it theta, sometimes we call it phi, but it's called phase. And we know that the angle always has some ambiguity in terms of you can always add a 2 pi to it or negative 2 pi to it. It doesn't change the actual value or the point, the physical point on the plane. But most people or most books set the convention that either theta is between negative pi to pi, or theta is between 0 to 2 pi. One of these two. I mean, we don't need to go add a 2 pi to it or negative 2 pi. Either we go a full circle or we go half positive, half negative, okay? And there is a very famous identity for complex numbers, which is called the Euler's identity. Excuse me. And it says that the exponential function, if you take it to the power of some number that is purely imaginary, so theta is a real number and j is a purely imaginary number. So e to the j theta can be simplified or written in another way as cosine of theta plus j sine of theta. So e to the j theta represents a complex number that has a magnitude of 1, because if I take the square root of real part, which is cosine squared, plus imaginary part, which is sine squared, I get 1, okay? Now, as you probably can guess, with the definition of the magnitude of z and theta, we can see that x is just the magnitude of z times cosine, and then y is the magnitude of z times sine. So if you factor out the magnitude of z, x plus jy becomes magnitude of z times cosine plus j sine, and we always write it in the e to the j theta form. So complex numbers have the x plus jy representation, that's the definition, but through the Euler's identity we can write them in the magnitude and phase format, and this phase has a periodicity of 2 pi, right? Adding a 2 pi to phase doesn't change the value of the complex number, right? Okay. Now, how do we implement this complex number class in Java? So we make it final so that it cannot be mutated or extended. And the way we do it, we just define a public complex object, a class which is final. And then it also has two variables, two private fields, right? Real part and the imaginary part. Real part is basically x, and imaginary part is basically y, and these two are real numbers. So we don't deal with j, we just dealing with a object, a construct, a data structure that basically keeps track of two real numbers, right? And then obviously we have a constructor that takes the real part and the imaginary part and assigns them to the real and imaginary. And again, these two are final. We can define them as final, which means that you cannot have a setter to set the value of real part. The value of real and imaginary part is only assigned at the time of creation of the object using the constructor, okay? And finally, the next basic thing to have after having the real and imaginary part is to be able to represent a string for this number, right? So we override the toString method, and the nice way to have it is that if the y is 0, we just want to show a real number x. If the real number is 0, and then we want to show either a positive or negative j times a number. So if y is positive, we keep jy. If y is negative, we represent minus j times the magnitude of y. Basically, the nice form is to always have the sign plus or negative before j. And for example, if we have j times negative 2, this is our actual number, we want to write this as minus j2 or minus 2j. Okay, so some people prefer to have the j at the beginning, some people prefer to have the j at the end. So if we put the j at the end, we don't need to care about this, so this is more like optional. Okay, and the same thing here. So this was an example or use case, and the next thing here, so if we have j times 2, we want to just write it as 2j. Again, if we set the convention that we put the j at the end, instead of having x plus jy, we have x plus yj, then we don't need to worry about this. And the next thing is that we want to be able to convert a complex number in form of a string to an actual complex object, and this is called parsing, and we discussed this when we look at the wrapper classes for real numbers in Java, like the double class, big capital double. It had a parse double method, and this is called the parser. You parse a string and create an actual double number. The same thing, we want to be able to do it. We give it a string that has a format of x plus jy or x plus yj, and or maybe x negative yj or x negative jy, and we write a method parse complex, and it returns a complex object. Alright, let's head to Eclipse and try to implement these. I'm going to create a new Java project. Let's call it demo complex Java 8, and next no dependency, the libraries of JRE, and order and export is okay. Demo complex, in the source folder I'm going to create a class called just complex. Alright, so we want this to be final, so no mutation, and private final double real part and private final double imaginary part. Okay, it complains that they have not been initialized. What we are going to do here, we're going to create a constructor double real double image, and then re equals real, image equals basically imaginary part equals image. If we want to make it clear, we can just add this also, but that's not necessary because there is no shadowing of the local variables. Now most people write the same name here, re and image, and then if you do that, then yes, you have to definitely use this, otherwise you're going to shadow your variables. But we're going to stick to real and image because it just makes it more readable. Alright, so as soon as this final fields re and image are initialized here, they can never be changed because they are final. Alright, and because the class is final, you cannot extend this class to create a subclass. So we have this, and we want to override the toString method. So basically a string representation of complex numbers, and the way we are going to do it is we'll go to source, implement override toString, and let's put this here. And then what we are going to do is define a string s equals empty string, and then if re equals 0, and in order to test for 0 we can just do this, but this for comparison of double numbers, this is not a good thing. We should have a threshold, but let's right now do this. So if real part is identically 0, we just put s equals j, or basically image plus j. We want to put the j at the end, image im, and eventually we return s. Else if image equals 0, return or basically s equals just re, but we have to convert it to a string, so we append it with a empty string. Else we just set the s as re plus maybe empty string plus image plus j. And the reason that I'm putting this here is that make it more clear. And then we return s. Now in order to test this, I'm going to create another class called test complex. I'm going to add a public method, the main method to it, and here I am going to create a complex u, or z equals new complex 2 and 3. So we create our complex number and then system dot out dot print line z. Let's see if this works. Yes, 2 3j. That's because I forgot to add the plus sign here. Now the problem here is that if this works is if imaginary is positive, but if imaginary is negative, it adds the plus and then there is a minus from the imaginary part, so we end up with 2 plus minus 3j, which is not a good way. So we have to add another if, else if basically imaginary part is negative. What we are going to do, we are going to set s as re plus or minus. We put the minus sign, math.abs image plus j. Okay, and then okay, now this should work fine. 2 minus 3j, and if we have plus, it should not. 2 plus 3j, yeah. So this works. And one nice thing that we can have is the j. So public static final complex just j equals new complex 0 and 1. This is nice to have, and the reason for this is for what I'm going to do next. So next, let's go back to the presentation. So far we what did we do so far? We created our complex number, which is a data structure, an object, and we assigned the real and imaginary part at the time of construction, and then we have a nice representation. So let's also check what happens when the real part is 0. It's 3j. If this imaginary part is it's minus 3j. Okay, now let's go back to the PowerPoint. So we discussed this, so I'm going to leave the complex parser for now, but we'll get back to this later. And we can define some built-in functionalities for complex math. So, and since this complex class is final, each of these methods returns a complex number. So we're not mutating the actual number, we return a new number. For example, if I have the method ABS, the absolute value or magnitude, which is the square root of real part squared plus imaginary part, I don't mutate the number, I just return a new number. So let's go to Eclipse and do this. So let's create a section for complex math, some simple complex math. The first one is public complex. No, the absolute value is a double. Public double ABS. So ABS basically returns a double value, and the way it do it is return math dot square root of re plus image times image. Okay, so the absolute value is a real number, so we return a double value for it. And the other functionalities are a more useful one is magnitude squared, which is x squared plus y squared, and then we have the phase, which we discussed has some ambiguity because of the periodicity on the phase, and the periodicity is basically pi. But we can confine it to 0 to 2 pi or minus pi to pi. So we can actually make sure that we limit it to minus pi to pi, and I'll show you how to do this. And we can convert the phase to degrees in order to, because the phase is in radians, in order to convert it to degrees we multiply it by 180 over pi. 1 pi degree is 180 degrees, 1 pi radian is 180 degrees, okay? And then we can add the simple functionalities such as plus, minus, times, conjugate, or a square root. Now a square root is a little bit complicated, but the easiest way to do the square root is through the phase representation or polar representation, as we discussed here, because the square root in this format is just the square root of the magnitude and then j theta over 2. Okay, so let's head to Eclipse and implement a few more. Public double ABS squared, and return re times real part plus image times image. Okay, and let's go and test it. Complex W equals z dot ABS and system dot out dot print line W. And that's because the ABS or ABS squared is a real number, so we should get a square root of 9 plus 1, 10, which is 3.1622. all right, so if I have a 1 0, I end up with 1 and 1. If I have j, for example, so instead of having this I define another number, complex w1 complex dot j, and then system dot out dot print line w1. So the magnitude of j is also 1, so we should get 1. Oh, sorry, this is 1j, and system dot out dot print line w1 dot abs. Now here we should get 1. Yes. Alright, so but the next thing is that operator overload. So we can add more and more complex functions, complex math, such as the exponential, which is the exponential of real part times the exponential of the imaginary part, and the exponential of the jy. Due to the Euler's identity, it becomes cosine of y plus j sine of y. So I'm going to write it here, Euler's identity. We end up with, and the sine becomes sine of real part cosine hyperbolic of the imaginary part plus j cosine of real part sine hyperbolic of the imaginary part. And for all of these we just return a new complex object and define it by its real part and its imaginary part. Okay, but the main or key thing here is to operator overloading, so that we be able to overload the plus, minus, times, division, which makes life much easier to deal with complex numbers. So let's head to Eclipse and I'll show you how to do it. Back to our complex class, we are going to do operator overloading. Now the first one is the assignment. So if I have public static, remember the assignment or the simple value of method should be should be static. What happens if I assign a value, double value v, to a complex number? I should basically create a complex number with real part v and imaginary part 0. Okay. What happens if I assign a value of method, basically assign a complex value? Return new complex v.re v.image. Now, as you probably can see, re and image are private fields, but I can access them for this complex number. And the reason is that private field, you can access the private field of any complex object as long as you are within the complex class. So private means as long as you're physically between these two curly braces, you can access the re and image field for any complex object. And that's the meaning of private. Okay. If you're outside of this class, for example here, you cannot access those two fields. But as long as you're physically inside this class complex object, you can access it. Now you may ask, why am I doing this, defining the value of method for a complex value? Basically, why should I assign a complex number to a complex number? I can just make them equal, use the equal sign. And there's a reason for that, and I'll explain it later. But right now, let's go and see if this works. In order to do that, I'm going to import from complex. I'm going to import static everything, which includes the J object that we defined. So I can do this. All right. And I can also do complex, the W2 equals 2.1. So the compiler doesn't complain. And if I check the value, print line W2, I should get a complex representation, which we decided to go with a real. Okay. Now what happens if I do the addition? So public complex add, and we want to add a double. And when we add a double to a complex number, it just adds to the real part. New complex, re plus v, and image. All right. Obviously, we have to also have a reverse. Add reverse. Doesn't change anything. But then the next thing is having an add for a complex. And again, re plus v dot re. Let's add this to make it clear, and this dot image plus v dot image. Okay. And same thing for reverse addition to a complex number, and it doesn't change. Okay, so addition is here. Now the reason I define this becomes very clear, because J is my basic complex number, and just exactly like the way that we write it in math, for example x plus jy, because the plus sign is now overloaded for complex numbers and for adding a double value to a complex number. So j is my base complex number, and then I can I can actually write this expression and be able to create a complex number. Now one more thing that I need is to implement the multiplication, because y actually multiplies j. So if I want to use j as my base, I have to also overload the multiplication. Public complex multiply double v, and we just multiplies both the imaginary part and the real part. Re times v, image times v. And we can have the reverse. it doesn't change anything. As a reminder, when I say multiply, it means this times v. When I say reverse multiply, it means v times this. Okay, and now let's go here. I have my base j class, and now I can write the intuitive way of working with complex numbers. This is how programming should be, how intuitive the programming should be when you're dealing with numbers. Okay, so complex w3 1 plus 2j. It works beautifully, and this is exactly how you write the complex number on a paper. Now obviously if I put minus, it complains because I have not implemented minus yet, but you already know how to do it. Let's make this like 1.1 system.out.println w3, and now we get a beautiful result, 1.1 plus 2j. So I'm going to add this here also. This is the beauty of operator overloading, for anything, any type of object that you can define a base object. And if you recall, for vectors we also define a base horizontal and a base vertical, and then once you overload the operations, plus, minus, multiplication, you can have a very intuitive and natural way of creating these objects. Obviously if I write j times 2, it's not going to complain because I already implemented the reverse multiplication. And the final thing that I'm going to do, I'm going to overload the subtraction, or basically all of these addition becomes subtraction, and we have to have subtract, and just a double value subtracts from the real part, and then reverse subtract complex number, reverse subtract the complex number, reverse subtract, it becomes v minus real part, and then the imaginary part is also is negative, multiplied by -1. Subtract from a complex number, and then we have reverse subtraction, v dot re minus this dot re. Finally v dot image minus this dot image. And now I can write minus here, and it should still work. Yes, 3 times this, it should work. And even I can write 2 w3 minus 1, and it should work. And you probably know how to override the division. Okay, so this is how we deal with complex numbers. We overload the operators, and then we can very easily and very intuitively work with these complex numbers. Now if you go to my MathLib class on GitHub, in the numbers package I have a complex and complex math. So complex is the base complex object. I've defined some 0, 1 plus j minus j and just j. And again, the idea is to have the real and imaginary parts and assign them at the time of creation, have a toString method, have some elementary math functionalities, ABS, phase minus to plus, degrees, and then having plus, minus, times, conjugate, for example, which you just multiply the imaginary part by 1. And then exponential, sine, cosine, power, equals. So equality, you have to check whether the real part is the same for the two objects and imaginary part is the same. But then the problem is that for double numbers you don't have a exact precision. Then basically it's better to compare it based on a tolerance, an error. If the real part and the imaginable is within this error, we assume that the two numbers are equal. Square root, and this is the parser that I talked about. You can look at it, but in order to show you how this works. And finally, this is the operator overloading. For assignment, remember the value of methods should be static. For addition, for subtraction, for multiplication, division, and negation. Now I've put some example here. So if I just run this code, complexity equals a double value, it returns 1, and then u is a 2.1 minus j plus 6. It shows that starting with the base j object, which is a base complex number, and using the operator overloading, we can create complex numbers. So here for a string representation, I'm using I. Most engineers use j. I guess I used I here, and I'm putting it at the beginning, not at the end. Okay, and then this shows that we have overloaded the plus, we have overloaded the division, and then this is the complex parser, parse complex, and it's a static method. And you see I'm giving it 0 minus I times 3.3, and it returns minus I 3.3. Okay, now if I put j, I believe it should still work. Yes, and again for the string representation it always uses I. But in the parser, which is a static method, parse complex, you can use both I and j. Alright, and in the complex method, it's just more functionalities like tan, cosine, arccosine, tangent, arctangent, cotangent, cosecant, power. And you see that all of these complex numbers are overloaded for division and stuff, so there is no problem just using the operators for the complex numbers as well. Okay, thank you very much for listening this. I hope you enjoyed it, and I'll see you in the next video.